welcome back everybody. I'm now going to move on to question 3 of the paper from 2022, and as you can see this question is on magnetic fields. So we'll start by doing part A, describe what happens when a charge moving at constant velocity encounters a constant magnetic field at angle 90 degrees to the charge's velocity, and show that the rotation frequency of subsequent motion is independent of radius and speed. Okay, so this is an equation that involves sort of motion in a magnetic field, motion of a charge in a magnetic field, and that is governed by the Lorentz equation. The force equals Q times E plus Q, that's not a vector, QV cross B. Now, there is no electric field in this question, it's not mentioned, so therefore we have no, that part of the equation is equal to 0. So we simply have F equals QV cross B. Now we're told that the magnetic field is at right angles to the velocity of the particle. So as a result of that, we know that V cross B is going to have the sign, or is going to have the magnitude of just VB. And because they're at right angles to each other, well, the force is going to be at right angles to both V and B. So the modulus of F equals QVB, and the direction is perpendicular to V. And if you have motion where the force acts perpendicular to the direction of travel, then you end up with circular motion. So the equation for the force required for circular motion is mv squared over r, and this must be our QVB is what produces this circular motion. So we can put those two equations as equal to each other. Now, we can work this out in a number of ways. For now, I'll just work out the radius. You'll see that there's V squared here and V here, so that V will cancel the square there. And if I rearrange things, I get mv over qb equals r. Now, the question asks us for the rotation frequency. Now, the rotation frequency, how do we get that? Well, if you have circular motion and constant, without at constant speed, we can use the equation V equals r omega. And remember that omega equals 2 pi f, and it's f we're asked for in this question. So I'm going to replace V equals 2 pi rf, and replace the V in here by 2 pi rf. So m 2 pi rf over qb equals r. I want to work out what f is then as a result. So f is going to equal, the qb goes across and goes to the top line. The 2 pi m is going to go to the bottom line. And the r, I can put in the r's if you want, but they're going to cancel out. So that's our equation for the rotation frequency. And as you can see, that frequency doesn't depend on r, and it doesn't depend on v. Okay, so we have our, that's part A done. Quite straightforward. Part B says qualitatively describe the motion when the field is not at 90 degrees to the charge's velocity, and also the impact of changing the magnetic field strength. Well, I'll do the second part first. We have seen from above that R equals mv over qb. So basically what that tells us, if B increases or decreases. I just realized I have to do the first part first. So we start out. Okay, so if the field is not at 90 degrees, if B and B aren't perpendicular, then there will be a component of V and that component of V which is perpendicular to V will produce a form of circular motion. The component that isn't perpendicular to B will produce linear motion. There will be no force in that direction if it's parallel, particularly if it's parallel to B. And so what we end up with is a spiral. We will still, because of this perpendicular to B, we will still get a force at right angles to V, and that will produce circular motion. And we have an extra linear velocity superimposed on top of that circular motion, which gives us not just a circle, but a spiral shape. So you get spiral motion. And what this equation up here tells us is that if B increases, the radius of that spiral will decrease. Again, if you want more information on this, I'd advise you to look at your notes. Okay, part C. And again, I'll just put the part C in front of the camera for you. Use the Biot-Savart law. Show that the magnetic field at the center of a circular current loop, current I, radius R, is given by mu naught I over 2R. Okay, so we're told to use the Biot-Savart law. And the Biot-Savart law, dB, this is given to you in the back of the exam, mu naught I over 4 pi ds cross R over R squared. And we have a loop like this, and we're going to show I traveling around the loop, and ds has to be in the same direction as I. So we can think of ds that way. ds is a tangent to the curve. And remember, ds represents a small section of the curve of the circle. And the Biot-Savart law tells us what that small segment of the overall loop, what contribution it makes to the magnetic field a distance r away. Now, we're interested in the center, so that distance is going to be capital R, the radius of the wire. And as I've said with previous questions, how do we figure out what the total magnetic field is there? We use integration to add up the contributions of every little segment of the wire all the way around. Okay. Now, as you can see there, ds cross R, ds is a tangent, R is radial, they are at right angles to each other. So ds cross R, the modulus of that is just going to be R ds, size of it. As for the direction of the magnetic field at the center, if you want to go and work out what that is, you use your cross product of ds cross R. So if ds is that way and R is that way, then the cross product, use the right hand rule, curl your fingers going from ds round to R. We get your thumb should point out of the page. So you have a dot there to represent the arrow coming towards you. Okay, so the magnetic field is going to be out of the page in the way I've drawn this diagram. Okay, so we'll fill our numbers in. What is it? dBr equals mu naught I over 4 pi, or ds over r squared. And we're going to simplify that down. dBr equals mu naught I over 4 pi r. All of those are fixed values times ds. To get, we now have to add up all our ds's. And of course, as we do, that means that b at distance r is the integral of mu naught I over 4 pi r ds. And it's around a closed loop. And of course, mu naught I and r are not dependent on s, on that distance around that you go in the loop, so that they can all come outside 4 pi r times the integral ds. And of course, if you integrate just a distance around the loop, you get the length of the loop. So that gives us mu naught I over 4 pi r going around a loop. I'm just going off the page there a bit, so I'll shift the page up. Integrate around the loop, it's the circumference, 2 pi r. And so we get mu naught I over 2 r. Okay, that is again not the hardest. Hopefully you're happy enough with that. Right, and on we go. Question D, part D. Use Ampere's law to show that the constant magnetic field inside a solenoid is given by mu naught In, or mu naught Ni is the way I normally see that written, but mu naught In. Okay, and we're using Ampere's law. So again, you need to know which law is Ampere's law. So I need to go to a new page here. So 3D 2022, Ampere's law. And Ampere's law is simply the integral of B dot ds around a loop equals mu naught I enclosed. Okay, so we can draw this is for a solenoid, so we can draw a solenoid. Okay, and we can take a section, a loop, and put it over that like that. Another way to look at that loop is to think of it as the current enclosed is that current coming around, and remember you can think of this as a slice. This is just a flat rectangle. It's not a three-dimensional shape. It's just a flat rectangle. And in each of those dots represent the current I. So in this case, you can think I've shown 4 turns of the wire here. So that would be 4I would be the I enclosed, where I is the current flowing. Okay. So we're going to say that the rectangle is L long, and there is no magnetic field inside the, there's no magnetic field outside the solenoid. There is only a magnetic field inside the solenoid. And the magnetic field is along that direction. So out here, there is no magnetic field, no B field. And in here, you have a B field, which we'll just, for the sake of this, we'll just say is going in that direction. So remember, ds aligns with, ds is a little distance element. It's not an area, it's a distance. So ds goes along the direction there, up there, round there, and down there. So inside the coil, ds and b are aligned. And that means that b dot ds, for this long side here of length L, b dot ds is going to be equal to b times ds. They are parallel to each other. You just multiply the two terms. For this one, b is 0. So therefore, that makes no contribution to this integral. And for this one here, b and ds are perpendicular to each other for some part of it. And if you do a dot product on two things that are perpendicular, you get 0. So therefore, we can say the integral of b dot ds round the whole loop simply equals the integral of b ds on the bottom side. That's what I mean by that side there or that side there. And b is going to be constant inside the solenoid, so that's going to be b times the integral of ds along that length. And again, it's a length, so when you integrate it, you just add up all the little bits, and that gives you the length of that part, and we've said that's L. So our integral here equals BL. Now time to look at the right-hand side of this mu naught I enclosed. So what's I enclosed? We're told n equals number of turns per meter. Therefore, number of turns enclosed, just take n and multiply by the length. And therefore, the current enclosed is the number of turns multiplied by I. So this is our equation for the left-hand side of Ampere's law. This is our relationship for the right-hand side. So now we can say, therefore, applying Ampere's law, so I enclosed is NL I mu naught. Cross out the L's, and again, very simple equation, mu naught Ni. And that's our answer. Right, we're moving quickly along. Let's get near my lunchtime. So part E, sketch a diagram of the forces experienced by a current carrying loop in a constant magnetic field and explain how this arrangement forms the basis of the electric motor. Okay. I'm not going to go through the whole explanation, but what we'll set up is just the basic idea. You have a north and a south. Magnetic field is going that way. I'll draw that in red. And we have a coil in here. And from the side, it may look a bit strange, but I'm just going to represent the coil by, these represent the two wires that are running perpendicular to that axis there. Okay, and on one side we're going to show the current going in on that side and the current coming out on that side. Then it's a matter of, with current flowing in those two arms, from the top view, by the way, from the top view this is what your coil is looking like. So this is the top view, there's your north, there's your south, and the current is, if it's an X there, it's going into the plane here, into that direction, and out there, and it's going around like that. So what can we say about the forces acting on either arm of this coil? Well, again, you use your the force on a current, on a charge, is F equals Q. Oh no, sorry, we can use a different equation. Sorry, apologies. I'll just check my notes here. It gives you the same thing, but F equals IL cross B. It's actually these are very similar equations. So AL cross B, L is the direction in which the current is flowing in. So that means it's going, for this side, it's going into the page. For this side, it's coming out of the page. Right? L cross B, going into the page, crossed with going that way. So if you use your right hand, going in, crossing to B, then my thumb is pointing in this direction here. So there's a force on this side down. And if I think now of the L coming out of the page for this side, L coming out, it's hard to show, but if you think of it as it's coming out and then the B field is going that way, so it's twisting that way, so the force is going up there. And so you get a couple, or a torque on the coil, which makes it rotate. And that's the basic idea of a motor. Okay, again, if you want more information, refer to your notes. And that's all I'm going to say about question 3. Part F talks about orientation energy and external magnetic field, and why do we refer to orientation energy rather than potential energy. I would ask you to refer to your notes because I'm not clear on, I haven't studied this in any detail, so I'm not able to answer that part. So I'm going to finish this video here, and that's question 3. If you have any questions on that, just send me an email. All the very best.